you, George, and Sherry.
Who's your honorary captain?
Good morning, everyone. How we feeling?
Right.
It is Friday. It's okay to be tired. Nice weekends are ahead. Anyone have any questions, comments, needs, concerns, etc.? Alright. In that case, our main goal for today is finishing up chapter 6. We're going to be looking at more collisions and specifically looking at them through the lens of the conservation of momentum. To kind of review where we left off. Wrong button. There we go. We began talking about collisions. We were first discussing impulse, the idea that, well, just the measurement of the change of momentum. If something speeds up or slows down, it has an impulse, and that implies that it is either gaining or losing momentum. This sort of thing tends to happen in collisions, a collision being just an event where two objects will exert force upon each other, and a certain amount of force exerted for a certain amount of time causes an impulse. That was one of the formulas for impulse that we looked at. And since two objects involved in a collision exert equal but opposite forces on each other for the same amount of time, two objects involved in a collision must undergo equal but opposite impulses. This implies that within a collision, however much momentum one object loses, another object must gain. To kind of give a very short example, let's say that you are playing a carnival game and you throw a ball in a stack of blocks and you just hope that the game isn't rigged. All collisions have a before state versus an after state, so I like to draw out before versus after. Before impact, where's all the momentum in this situation? In the ball. If the ball has mass and velocity, which I'm just going to call VI does not equal 0, then this object should have some amount of momentum. What about these things, if they're sitting still on the Carney's desk? Not moving. If their velocity is 0, no momentum. So here VI is 0, as opposed to is not 0. So now however much mass that is, if it's not moving, it doesn't have any momentum. Now after impact, insert poorly drawn particle effect. Got the ball, got all the blocks now scattering to the wind. The blocks don't have a velocity of 0 anymore, do they? The goal is that they don't. The goal is now they have a velocity and they are now moving away from the stack. So now those blocks have momentum. They must if they have mass and they are moving. But do you expect the ball to be moving at the same speed it was moving at earlier? No, because in order for the blocks to now have momentum, the ball had to lose some. Momentum's not just spontaneously created on impact, it's transferred from one item to the other. And so if the blocks now have some, the ball must have less. And you've probably noticed that when one thing strikes another thing, often it isn't moving as fast afterwards. So that is meant to be evidence of a transfer of momentum from one to the other. But the thing that we're about to prove, or try to demonstrate, is that the amount that one lost is the same as the other gained, implying that the total from start to finish is the same. And we call this the conservation of momentum. The idea that there's a certain total amount present initially, let's just say 10, for example. There's 10 units of momentum present on this initial side. And initially, the ball has all of it. After impact, momentum can't be destroyed, it still has to be here, but now that 10 units are going to be split between every item present. So if the ball initially had 10, it might have to give 1 to each block, and it only has 4 left over, well, however many left over. This law says that the total amount from start to finish has to remain the same. It's just going to be distributed differently. This is again kind of backed up by the idea of Newton's second and third laws. If the objects are exerting equal and opposite forces on each other, they'll have equal and opposite impulses. However much one loses, the other must gain. That's a concept. How we feel so far? All right. This equation, because that is technically an equation, says sigma rho initial equals sigma rho final. That is again literally total momentum on the initial side must equal the total momentum on the final side. The total between the two stages is the same. That's what these two tens are. The total amount of momentum on each side, just distributed differently. And that equation is going to be our starting point, looking at a few more collision type questions today. Any questions before we apply this new formula? All right. I'm going to move away from from this carnival game. I guess the next example could still be one. And move on to something that I have pre-prepared numbers for. We are going to throw a shuriken at a piece of wood. I watched a ninja movie recently and we just felt inspired. I did go with this particular set of items for a reason, namely because the piece of metal is going to stick into the wood. That will become important later. So, in this version of events, we are going to be throwing a throwing star at a piece of wood, bless you. The star in question has a mass of 100 grams, and we throw it at an initial velocity of 25 meters per second towards this piece of wood. Said piece of wood has a mass of 16 kilograms and is not initially moving. I'm kind of envisioning it sitting still on a fence post. And this is before impact, before the star strikes the wood. And now, as I said, all collisions have a before state versus an after state. What do you feel like the after state would look like? What do you feel would be zero? It's okay. The final answer we're fishing for will be very close to zero. I think you're intuiting something good there.
So the meters per second would be or the momentum of it would be 2.5 meters per second.
Yeah, we are going to find that the total initial momentum will be 2.5, and that amount must remain consistent all the way through. The thing I'm asking first, though, is physically, if you saw this heading towards this, what do you think it would physically look like after impact?
It's going to be stuck.
It's going to be stuck. That's one reason I went with this thing. just going to very poorly draw this piece of steel embedded in the wood. And after that happens, just based on your experience, what would you feel the final velocity of the log and the star will be after this happens? Just based on intuition.
0.
If not 0, then probably very slow. Maybe enough velocity for the log to fall off the fence post, but you wouldn't expect a very big final velocity, would you? We're going to prove that. We're going to show the math for how that works, for where that sense that you're intuiting is coming from. Since we don't know for certain what the final velocity is, I'm just going to list it as question mark. Note that the object's separate masses are unchanged. It's still 100 grams of steel and 16 kilograms of log, so those aren't any different. So M1 is still 100 grams, M2 is still 16 kilograms. What's different is now they're stuck together and traveling at some different, likely dramatically reduced final velocity. Note though that since they're stuck together, it's the same final velocity. They're going to share it. They're stuck. They have to travel at the same rate. It's going to be relevant later. So this is just our before state versus our after state. And we are going to use the conservation of momentum to determine what that final velocity is. Conceptually, how does the setup feel? Mostly nodding, okay. So, what conservation of momentum tells us is, there's a certain total amount of momentum present in this two-object system before impact. And that total amount will remain constant even after impact. It'll just be shared and split differently between the two items. So let's figure out what that initial amount is. This, again, the equation from the previous slide says sigma momentum initial equals sigma momentum final. This is the total initial momentum. And that means that to figure out what this is equal to, we need to take the two momenta of the two objects in this before stage at these initial velocities and add them together. This is asking for us to find their initial momentum levels and add them together to create the total within the system. And since there's two objects, that's going to be two different initial momentums, the star and the log. I'm just calling star object 1 and log object 2. Does that sound okay? If you wanted to, you could use the word star and log instead of 1 and 2, as long as you're consistent all the way through about it. And again, we're going to find their initial momenta, add them together, and that will tell us how much total is present in the system both before and after impact. Now on the final side, and if I look very briefly at the right side of this equation, it's asking for almost the same thing, total momentum final. And so rather than their initial momentum levels, this side is asking us to add together their final momentum levels based on their different final velocity. Same two objects, but instead I'm writing row 2F and row 1F. And whatever each object's individual momentum is, what this law says is that the total of both finals must equal the total of both initials. How I feel so far? All right. Now, how do we go about calculating an individual object's momentum? So, if we want object 1, being the star, we want its initial momentum level, we want to use its initial velocity. Its mass doesn't change from stage 1 to stage 2, its velocity is what's changing. So we want to use initial velocity times its mass. So instead of rho 1I, I'm now going to write in the star's mass times the star's initial velocity. Star's mass is 100 grams. Is that what we want to write? How many kilograms is that?
21.
Very good. Not a very massive object. It'd be a lot harder to throw if it was. Now, how much momentum does the log have on the initial side? 0. We know that because it's not moving. I'm still going to write down though. Mass times velocity, 16 kilograms, which is already in the right unit, times 0. So that's just going to go away. This tells us that initially, the star has all the momentum in this system, kind of like previously the ball thrown at the blocks. All the momentum that's here is physically here, and the log doesn't have any of it yet. And that's our initial side. Feel good about this half? Alright. Now in the final half, we have the same two objects, so it's the same two masses, but they each have a different final velocity to their initial. They are both going to be moving at a different speed. The star is going to drop from 25 down to something, and the log is going to increase from 0 to something. Question?
For the first part, where it says like 0.1 and 25, is that like the initial, what does this mean?
Yeah, sorry, that's mass 1 times velocity 1 initial, based on this formula. You know what, if it'll help for your notes, I should be more thorough. Taking this equation and plugging it in for all of the rows present here, rho 1 initial would be mass 1 times velocity 1 initial. Rho 2 initial would be mass 2 times velocity 2 initial. On the final side, rho 1 final is mass 1 times velocity final. Rho 2 final, mass 2 times velocity final. I have not specifically labeled velocity 1 or 2 final because they have the same VF. They're stuck together. It's going to be the same VF in both positions. If it wasn't the same VF, you'd need to be specific, but it is the same VF. So we can make it one shared variable. The same VF in 2 spots. Does that help? All right. I'm running a little light on board, so I'm going to take this and continue over there. Again, plugging numbers into that left side again. Mass 1 is 0.100 grams. Velocity 1 initial is 25. Mass 2 is 16 kilograms. Velocity 2 initial is 0. On the final side, we have the same 2 masses, but being multiplied by a different shared final velocity. So M1 and M2 are the same between both sides. Mass does not spontaneously change by itself, but the velocity is changing. You don't know what to, but we're going to find that out. How do we feel getting to this point? All right. Now at this stage, there's only one unknown, just VF. It's in 2 different spots, but it's the same unknown, so algebraically we are good to try to solve for it. let's look at the left side first, because there's nothing unknown over here. We can just find a number for the left. What's 0.1 times 25? 2.5. And what is anything times 0?
0.
Yep. Once again, the star is bringing all of the momentum to the party. The log didn't bring any of its own. Now on the right, same variable in two different places. What property of math can we take advantage of here? Technically, yes. Also, technically, yes. Someone say Twilight Zone? Oh, yes, thank you, sorry, my ears were not working there. Combining like terms, very good. Because both of these are just a number times the same unknown. So these can add together normally. You can add them together normally. I prefer myself to think of it as using the distributive property. Distributing the VF out of both terms and leaving behind 0.1 plus 16. But this is absolutely combining like terms. And this would add up to then 16.1 times VF. That works as long as it's the same variable and nothing has a squared or anything on it.
So then you just divide by 2.5 divided by 16.1.
Correct. Left side simplifies to just 2.5. Right side's gonna simplify to 16.1 times VF. Divide both sides by 16.1. And if my memory serves, that should make the final velocity approximately, tiny bit of rounding, 0.155 meters per second. Not very fast. The log might twitch slightly, maybe it'll fall off the post, but it will twitch. It doesn't drop just straight to 0. The momentum, it is absorbing momentum from the shuriken. It is going to move slightly. How's the math part feel? All right. So that's now their shared VF. I'm going to take that number and I kind of want to prove just one more quick thing before moving on. I'm going to take that VF and prove that the two objects have equal but opposite impulses. So I'm just going to calculate the impulse of each object real quick. I have two erasers to keep one on each side of the room, yet they somehow still end up together and not where I want them to be, which is usually my hand. I'm just going to rewrite the VF part up here. All right, so very quickly, I'm just going to find the impulse of the two items. M1 times delta V1. That would be the throwing star's mass times the throwing star's change in velocity. They both have the same VF, but they have different VIs. The star ends here, but it began at 25. Separately, the log mass of 16, same final velocity, but it started at rest. So that's minus 0 instead of minus 25. And if my memory serves, please correct me if I'm wrong, we get approximately negative 2.45 for the star and positive 2.45 for the log. There might be a slight difference because of rounding, but please let me know if that is not what your calculators say. Again, my intent here is equal but opposite impulse. The star loses this much, and the log gained the same amount. Which which also means that the star only has like 0.002 units of momentum left. It literally gave almost all of it to the log, and the log is only just barely budging as a result. But 16 kilograms of wood is pretty heavy. So how do the concepts of the collisions and conservation of momentum feel? All right. That's not just summarizes what I already said. So, one more thing I want to cover today. Notice I haven't acknowledged that word inelastic up there yet. Is anyone wondering what that means? That term describes the type of collision that this is. Because even though momentum is conserved in all types, I want to make this clear, this is true no matter what. There are two different types of collisions. Real quick point. I do promise that momentum is conserved no matter what, even if it doesn't look like it is. As an example, I am now going to cause a collision between this deflated soccer ball and the earth. I want you to ponder where the momentum is going in this collision. Where'd the ball's momentum go?
Into the ground.
Into the ground. Do you see the ground moving as a result of this? No. Is momentum still conserved?
Yes,
Yes. Why?
because the floor took an impact.
Floor took the impact, and what is the mass of the floor and the earth it's sitting on? It's huge. It's too big. 5 units of momentum going into the floor is not going to make the planet budge because the planet's mass has 11 zeros on it. So the momentum is conserved even if it doesn't look like it is. Kind of the same as Newton's third law, equal and opposite forces even if it doesn't look like it is. Separate from that, there are still two different types of collisions. Those being elastic and inelastic. I will be very specific when I'm trying to enunciate those two words. You've noticed the difference between these two types of collisions, though, I guarantee it. I will now demonstrate these two types of collisions by throwing two different objects at the wall. This basketball is freshly reinflated. This soccer ball is freshly deflated. So, two pretty different objects, given that fact. And I'm going to throw both of them at the wall one at a time, and I want you to notice the differences between those two collisions. First, the basketball. So, impact with wall in 3, 2, 1. What type of collision do you think that was? Elastic. Now I'm going to throw the deflated soccer ball. Impact in 3, 2, 1. What type was that? Very good. Conceptually, you already know the difference. You can identify it by sight. Elastic collisions have elastic objects in them, and so the objects tend to bounce off from each other. The physics definition of elastic, an object is elastic in physics if it is able to change its shape and then go back to normal all by itself. It's kind of hard to tell with a basketball because it happens too fast to notice. So I'm instead going to demonstrate with this thing. When an elastic ball strikes something, it changes shape on impact. If you were watching this with a high-speed camera, you could see the object blorp, technical term there, on impact. And an elastic object is able to return to normal all by itself. This means that in doing so, it tends to kick off of the floor or the wall harder than it would if it didn't return to normal. The act of going back to normal involves force, so again, it's going to kind of kick off of whatever it hit, return back to normal, and as a result, elastic collisions tend to be more high energy, more chaotic things bounce away from each other at greater speeds. The physics definition of an inelastic item is one that, and again I'm using technical terms here, if deformed, meaning its shape changes, if deformed, it does not go back to normal all by itself. The deflated soccer ball, if I, again, technical term here, blorp it, stays blorped. Doesn't spring back to normal all by itself, so it does not kick off of the wall. Instead, you have the impact, and then it just falls. Inelastic collisions involve inelastic objects. The objects involved will crash, they will crunch, and they will stay crunched, and then they tend to stick together as a result. Inelastic collisions end up being less chaotic. The objects don't bounce away from each other. They tend to stick together, have a shared final velocity, and the whole situation is, again, less chaotic, less energetic. Things tend to be slower afterwards as a result. Momentum still conserved. That's the same general rule for all types, but there is still a difference that we will be exploring today and also in lab next week. So if I hadn't mentioned it yet, next week's lab is collisions. You will be running one thing into another thing and doing math. And I want to at least briefly demonstrate some math looking at the two differences here. Again, the main mathematical difference for right now is that elastic collisions tend to have different final velocities. The two objects will have different final speeds because they spring off from each other. Even if it's the same number, different directions means a different sign, and that means different velocity. Inelastic objects tend to stick together, and that means that they will have the same final velocity. And we will quickly do some math to demonstrate the difference between the two. But to try to make that difference clear, these two collisions are going to have the same starting point. We're going to lob a 1 kilogram item at 10 meters per second towards a second 1 kilogram item. And that's going to be the same whichever type of collision we look at. So we're going to have the same before state to better show the differences between the two. Any complaints if I erase this to replace with the new version? All right. Math's going to look very similar. All collisions do, but I'm also just going to change the picture. Also, any issues if I erase this? I'm going to need this part of the board too. All right. All right, so our new before state, we're gonna lob a 1 kilogram ball at a second 1 kilogram ball. So the two mass numbers are going to be the same this time around. The first object's initial velocity is 10 meters per second. We're gonna throw 1 kilogram ball at 10 meters per second towards a second 1 kilogram ball that is starting at rest. So mechanically very similar to the previous question, but different masses and a different VI1. And the first version of events that we're going to explore, these two objects are going to be made out of putty or clay or Play-Doh, your choice. And they're going to stick together. They're going to share a unified final velocity because if these are inelastic, silly putty-like items, they're just going to blorp together and be stuck. So, poorly drawn image of two balls of clay fused together. Same two masses, just united. And as before, some currently unknown shared final velocity. Now, the setup for these types of collisions will all look very similar. Momentum initial equals momentum final. Find the momentum of each item before versus after, plugging in different masses and velocities here as required. So instead of, 100 grams and 16 kilograms, we've just got two different 1 kilogram items. And that mass is consistent from start to finish. And our two initial velocities, we've got 10 for the first objects and 0 for the seconds. And they will once again, as before, share a currently unknown but common VF. Any questions or issues with setting this up, how it is similar from the previous example? All right. Left side, 1 times 10 is 10, 1 times 0 is 0, so the left side is just going to become 10. Right side, we got 1 VF plus 1 VF, which is just 2 VF. And so, in this version of events, the shared final velocity is 5 meters per second. They fuse together, they're now sharing, bless you, the original 10 units of momentum. They each now have 5 units of momentum so that their 1 kilogram masses are both moving at 5 meters per second. You could think of it as, instead, comparing 1 kilogram moving at 10 meters per second to 2 kilograms moving at 5 meters per second. So they are now evenly sharing the momentum that the first object brought. That's the inelastic version. Questions? Concerns? All right. Let's now look at the elastic version. So instead of clay or something that's going to fuse together, let's say that they are both basketballs or similarly elastic sport equipment of your choice. Same before state, but I'm going to give you a different after state. In this new after state, the second object bounces off from the first as the first comes to a complete stop. That is informing us of what the first item's final velocity is. So our new after state, mass 1, still 1 kilogram, but its new dedicated final velocity is 0. This is a poorly drawn impact effect. Object 2, meanwhile, is going to rocket away at some other unknown VF. They don't have the same VF in common anymore. Again, this tends to be the case in an elastic collision where things ricochet off from each other. Even if they did somehow have the same number, it would probably be in opposite directions, and that's still a different VF for that reason. So again, main difference here is different VFs, and thankfully we already know what one of them is. Math will still look very similar, because literally I've changed nothing about the initial side. The initial half will still be mass 1 times velocity initial 1, plus mass 2 times initial velocity 2. So there's still 10 units of momentum present. But now, object 1 comes to a dead stop. Its final is 0. object 2 will have a different dedicated VF. This means that object 1 has lost all of its momentum. It's just gone now, and therefore row 1 final is just 0. Meanwhile, row 2 final, well, that'd be 1 times V2F, which ultimately, if we were to solve for that V2F, would just come out as 10. This implies that ball 1 lost everything and gave all of it to ball 2. Same total, but now completely donated from one to the other, rather than shared. This situation, I'd say, is most commonly observed on those Newton's Cradle desk toys. You know, the balls hanging from strings where you pull one back, it collides, and all the momentum totally transfers through to the other one, and the first one is now stationary. That is exactly what this is. So again, the key difference between the two types is either shared VF or two different VFs. Now that, first of all, questions. All right. Now, I will usually tell you what type of collision it is. Either I will tell you it's inelastic and it's the same VF, or elastic, give you one of the VFs to find the other. Momentum's still conserved across both, but I'll make sure you have everything you need to find what I'm asking you for. This one difference can result in like kind of a domino effect of smaller changes from that point onwards. This is what lab next week will be exploring, so I just kind of want to mention it now to get it into your brain. In this scenario, they're both now moving at 5, so ball 1 dropped from 10 to 5 and ball 2 increased from 0 to 5. So that's a change of 5 meters per second for both. Just one's getting faster, one's getting slower, but it's still a net change of 5 for both objects. They would still have equal but opposite impulses, but that impulse would be either positive or negative 5, depending. Over here, ball 1 goes from 10 to 0, and ball 2 goes from 0 to 10. So that's a change of 10 meters per second for both, and so the impulses over here would be either positive or negative 10. Changing the collision type affected the size of the impulse. It's still the same impulse between both items, but the elastic collision just has bigger impulses. And that is an unfortunate side effect of elastic collisions. The impulses are bigger, and that means I'm just running out of board. Bigger impulse means more force is involved. Assuming that the times are all still pretty small and pretty consistent, most collisions happen in under a second. More impulse means more force. And that's why elastic collisions tend to be more chaotic. There's literally more forces involved as object 2 kicks off of object 1. Whereas instead, over here, they just combine and deal with it together. The physical act of returning to your original shape and kicking off of the other object literally adds more force in the equation. And so these collisions, higher energy, more chaotic, more forces are involved, and that means they're more dangerous. You might think more fun, but unfortunately in physics, fun tends to correlate with danger. And that's kind of what lab next week will be about. And how this then applies to car manufacturing. Questions? All right. In that case, we're done for today. That means we're done for the weekend. Please let me know if you need anything over the weekend. You should, again, still be looking over your homework, using it as test prep for 2 weeks from now. Let me know if you need anything, have any questions, etc. But most importantly, have a great weekend.
Yeah.